Hello everyone, welcome to a slightly different format of Kwyll video, update video this week. We're going to get into a little bit more technical detail. I've been working on a particular feature that I think warrants some more explanation. So if technicalities or code aren't your thing, feel free to move on. I won't be at all offended. But if you're at all interested in understanding a little bit more about how the logic or some change in direction on the way the logic works is implemented internally, stick around and we'll get into the weeds for a little bit. So a little bit of background about why I'm making this change. It's around the logic. Don't worry, it's nothing that affects the user. It's all under the hood. So all of the work anyone's been doing with the logic up until now will still apply exactly the same. Nothing changes. It's just how it gets exported onto the spectrum and runs on the spectrum. And it's not actually 100% guaranteed that this is the direction it's going to take. It's an experiment. It's very much an experiment at the moment. So we'll see where it leads. But the background behind it is I recently, last weekend, attended Crash Live up in Kenilworth, near Warwick, which was a fantastic event. Highly recommended to anyone who gets an opportunity to go to one of those events. It was great fun to see so many people interested in retro tech, in the spectrum in particular. To see the talks from some people from influential people from back in the day, like Sandy White and Bob Macmillan and so on. It was quite nostalgic to hear their stories of their experiences of game development back in the early or the 80s and 90s, how they compared to my own experience at Incentive. It was a really good fun experience, so highly recommended if you get a chance to go next time. And just on that topic, I'd like to make a request to anyone out there that is aware of similar events that might be going on, particularly around the country. I'm not really keen on travelling too far, but if there's an event that's retro focused that you're aware of, drop a comment in the comments below, because I'd love to see if there's any more that I can attend and experience. So if you're aware of some, just let me know. So anyway, back to the reason for this change. So I was chatting to someone at Crash who recognised me from these videos, and we got into a discussion about the topic of memory use and how Kwyll will or does or might track memory use and make sure that the user who's designing the game stays within certain constraints. And at the moment, to be perfectly honest, it's very difficult to track. It's virtually impossible. And the reason for that is the logic in particular is exported as C code, which then gets compiled using the Z88DK compiler toolchain down to Z80 assembly. And there's no way ahead of time of predicting how big that code is going to be. It's an optimizing compiler, so while it's predictable in that if you run the same code through each time you're going to get the same output, it's not predictable. So I can't look at the logic tree and say 15 nodes is going to be 300 bytes. I can't do that in the current structure. So that's a bit of a problem. And when asked what it currently does, the answer is quite simply: you build your game in Kwyll, you export it, compile it, you run it on the emulator. If it crashes, you're using too much memory. That's really the only measure you've got at the moment. I can track various things about data usage in other areas, so sprites, tiles, objects, that sort of thing, that are fixed data structures. I can provide information back, and I do in various places in the tool. But that doesn't help if you end up producing a lot of logic, and that just pushes you over the edge. So one of the things I've been thinking about doing, or thinking about exploring at least for a while now, is changing that basic mechanism. So I decided very early on in Kwyll to export to code and have an external compiler compile it, because it felt like a good way of ensuring that you only export or you only build into the game what is needed. So it exports the logic as written effectively in Kwyll using the drag and drop tools, and only exports what you need. So if you're not using certain features, they just don't get compiled in. And I felt that was a good way of ensuring that it stayed within certain constraints. So now I'm considering the relative value of that knowledge, that you're generating a game that doesn't include lots of things that aren't needed, versus predictability and being able to know how much space you've got, how much room you've got to work with, where you need to optimize, where you need to cut back, where you need to make changes in your game, and so on. So again, this isn't a decision that's been made, it's a decision that's being explored. So this idea I had was to switch the logic over to a data-based paradigm, as well as the rest of the system, so that everything that gets exported from Kwyll is data. And the library, the Kwyll library, which is already existing, which does all of the things like it includes the SP1 sprite library, it manages objects, it manages rooms and screens and collision detection, all those things, is extended to interpret the data that's exported representing the logic and execute the logic purely from a data perspective. So it's very easy then to get a clear understanding of how much additional memory a logic graph will produce, because I'm in complete control of the data that gets exported. It's not going through a compile phase, it's just a block of binary data. So what this amounts to in concept is a virtual machine running on the Spectrum, interpreting bytecodes and running compiled library code based on the bytecodes it gets. It's something I've got some experience of before. I've done it many years ago in the Axis RenderMan renderer, although that was a far more complex virtual machine. It was a SIMD virtual machine. So I have some experience of building this sort of thing. And after the conversation at Crash, I decided to have a tinker and bring this forward and have a play and see what I could do. And I've got it somewhere where it's operational to a degree. It doesn't have all of the features of the virtual machine running, and it doesn't convert all nodes at the moment, but it does enough to demonstrate that I can show you what it's doing, and to start to get an idea of what the performance and memory implications of this approach might be. I think I'm going to have to get further than I currently am to get a definitive answer of whether it's the right solution or not, but well on the way. So what I wanted to do was very quickly just go through how it works, what it looks like under the hood to a degree, give the more techie people out there a bit of insight into how it might look and how it might work. Of course, happy to get any feedback or any ideas or thoughts from people who are experienced in building Spectrum games. If you've got any ideas about how I can do this better, or things I should be avoiding, is this even a good idea? I'd love to hear it. So the format of this video is slightly different. So before, I've always had a single window on screen at any one time, and I switch between windows, but I'm going to have a whole screen here so I can jump between apps. So bear with me if it gets a little bit clunky. So this is the new branched version of Kwyll. It doesn't look any different, and it shouldn't do, but I've got let me just show you what this sample is. It's some slightly modified version of the brushes test, if anyone who's been using the early access. So it's basically just a simple player, left, right, up and down controls, a couple of objects with some collision, and they are using the brushes, but it's irrelevant for this particular thing, and a key, which is another object that can be collected and moved off to the side or off screen. So if we look at the code for the object, that's where all the code is in this example. It's fairly simple. We've got some movement logic there that moves the object, checks to see if it collides. If it collides with a key, do a modify tiles, which doesn't do anything at the moment, and then transports the key off screen. So that's the logic that we're exporting. So before, that would have generated, let me show you what it would have generated. So this is the code, the generated C code for that logic graph as of version 0.69, which is the latest available version to the earlier adopters. So you can see we've got a whole bunch of generated code in here, which calls a library function to move the object, calls another library function to check for collisions, and then if it's collided, does some things like modify the tiles and moves the key off screen. So this is all generated and will be compiled by the Z88 DK compiler. So what we're doing now, that's the old style, and this is the new style. So this is the header file exported from this version of Kwyll, and you can see we've got, instead of C code, we've got a byte array, which is the code in the VM, the virtual machine that I've implemented as part of the Kwyll library. So while these look like instructions, they are actually just enums. So there's an enum in the Kwyll library that lists all the opcodes, and it's just convenient to print those out as part of the export, so that I can see what code is being generated. It looks almost like an assembler rather than just numbers, which are difficult to interpret manually. So it's a stack-based machine, for anyone who knows what that means. There are various different ways you can run low-level machine code in emulators or even on silicon. One way is to have lots of registers or a number of registers, and you pass values between things based on registers. Another way, a much simpler way to implement, certainly in code for an emulator or a virtual machine, is a stack-based solution. So what this does is it has a memory, an area of memory that each instruction can push values onto that stack, and the pointer moves down, and then they can pull values off that stack. So it's just like literally a stack of paper, and you push a value onto the top of the stack. The next instruction might pull 1, 2 or 3 off the stack and do something with them and push something else back on. So that's basically how it works. So I'll just go very quickly through this program. I won't go into too much detail, but we've got each line here is a single instruction to the VM, and it starts with an opcode, which is the text, and then 0 or more additional bytes, which are the fixed data for that particular instruction. So what typically happens is, where you have an instruction that has fixed data passed in, it maps to a node on here that has values that you can set within the node, but don't have that don't have ports coming in that you can feed in from elsewhere in the graph. So the controller node is a perfect example. It has no input ports at all. Everything that describes what this controller node does is fixed at the time of design. You enter these values here, and you choose the mode here. So that maps to this information being passed in here. There's nothing being pushed onto the stack. It's all in there, in those 3 bytes. So this first this first instruction will read one of the directions from the controller node and push the result onto the stack. So this one is, I'm not sure what this one means, but this is the entry in the list. I can't remember off the top of my head, and this is what will be pushed onto the stack if it's true. So we've got 1 and -1 there, which you can see mapped to these 2, -1 and 1. So this will push a value onto the stack. So you've got 1 value onto the stack, whether this particular key, 1 will probably be right, is pressed or not. And then this will push a further value onto the stack, and this will be if maybe left. So left and right, it's either left or right or up and down. And then the add instruction it has no additional parameters. It's purely based on the values in the stack. So this has pushed 1 value onto the stack. This has pushed another. So the stack now contains 2 resulting numbers. The add will pull both of those off the stack, resetting the stack back to the top again, add them, and then push the result onto the stack. So you can see how a stack-based machine works. And then we go on and we've got more instructions here. So this is a push B, which is 0 for the reference. So this is actually the code that's generated for the instance data node. So if we go and find the instance data node here, it can have a reference come in, but this one doesn't, so it just pushes 0, which tells the VM to use the current object, the object on which the code is running. And then inst data will pull the third value from inst data, which is x, so let's put in the x. And it will push that into the stack. So now we've got the result of the add on the stack, and we've got the result of the inst data on the stack. And then the add will add those two and push the value onto the stack. And similarly it goes down here, so this is for the other direction. This will be y and the up and down, or left and right. And then finally we add all of them together to get our x and y. And these feed into the move object. So this is the code for the move object. Again, there's no reference coming in, so use the current object, and these are not the x and y positions as you may think. These are this is related to how it handles collision. So the x and y position that the move object needs to move to have been pushed onto the stack by all of this. There will be an x and a y pushed onto the stack. Move object will pull those two values off and the reference, which is 0 in this case, so it will use the current object, and it will attempt to move that object to those coordinates. Now you'll see from the graph here that we've got this flow out that gets followed if the move results in a collision with another object, and we have a flow which will be followed, but also we have this variable, this output port, which is a reference, and it will hold the reference to the object that we collided with, the first object that we collided with, which is used in two places here. So it's used in the is type to see if it's a key, and if it is, then follow through, modify the tiles and transport the key out of the way. And it's also used further on in the transport to actually tell the transport node which object to move off screen. So we need this in multiple places in the rest of the code. So the way that's handled in the new system is using this data block down here. So when compiling, any node can request of the compiler some space in a data block that exists after the code, and it will get back an index into that data block that it can use for various things. So what's happened here is this move, when compiling this move, it's asked for some space and it's been allocated 2 bytes, a 16-bit value, and it gets back 0 as the index because it's the first entry in the data. So that's what this information here is. It's telling the move object opcode that when you do your collision detection, if an object is collided with, put it in here so we can use it later, which is what happens straight after. So the read W will read from the data block at a particular offset. So this is reading back from the data block and pushing it onto the stack. So now we've got a value on the stack which is either 0 if there's no collision, or a reference to the object that was collided with. And then push will push 0 onto the stack, and then EQ will just pull the two values off the stack, compare them for equality, and set a flag to say whether they are or not equal. So in this case we're reading the value that came back from the move collision check and 0, and we're checking to see basically if the collision was 0, and there was no collision. If it's true, it'll jump 24 bytes ahead, which takes us back down to this ret here, so jumping over this bunch of code, because if it's 0 it hasn't collided. Then it'll read that value back out again. So this is where we see the importance of having it stored in data. So we've got it stored here, you can read it out and use it multiple times without having to recalculate it all. So it's reading that back out, pushing it back onto the stack again, and then the is type opcode takes a single value, because again if we look at the structure of the node here, there's no input port for the type that you're checking against. You choose it from the list, so it's fixed. So we're checking for type 1, which is the key, and this will set the flag directly, so it's equivalent to the EQ command. It'll do its comparison and set the true flag if it passes. So this is now going to jump if it's not true. So JNT and JT is jump if true, JNT is jump if not true. So if the type of the object that we've collided with is not a key, then jump over and it takes us back down to here again and skips the rest of this. And then if it is true, so it is a key and we've collided with it, then it'll do that, which is pushing a bunch of stuff for the complex modified tiles node and calling the modified tiles node. And the value on this one is the state of these, which are fixed, so the ignore and clear. So these can all be brought in, so these are the values that are pushed onto the stack, because they can possibly be delivered from elsewhere in the graph through other calculations or other sources, whereas these flags here and this one are fixed in the node. You set them and that they can't change at any point after you've saved the file. So that's the 20 there, just to set flags. And then after that's completed, it pushes 300 twice, 12C in hex is 300, which is the transport object. And this time, instead of pushing 0, which we've done when we did the move up here, which indicates that the move should use the current object, we're actually going to push in the reference that the move object reported back. So this will be the key, and then transport that object to those coordinates and then return. So you can see how it's structured, how it works. It's a very simple, as I say, very simple stack-based machine with a few basic instructions: add, push, multiply, divide, push and pop, all those things, and then a few very complex instructions which map directly to the core functionality of Kwyll: move, transport, modify tiles, and so on. And you can see down here it outputs at compile time a simple analysis of where the data is going. So there's 79 bytes worth of actual code, which is this up to there, and then there's 2 bytes of data assigned for a total of 81 bytes. So for comparison, I've got the version here, which is exported as C code, the very same thing exported as C code, and compiled using Z88DK. And I've written a script in Python that will analyze the map file that gets generated by, or can be generated by, the Z88DK, which holds a whole host of information about different addresses. And from that I can determine with some accuracy how big certain parts of the code are using this tool. So I've got this analyze map, which will read in the map from that old version, and this is all the code that gets generated, including stuff from the Z88DK, SP1 and so on. But we're interested in the player always, so if we search for player always, we can see we've got this function here is at address 70D4 and critically is 272 bytes long. So that C compiles down to about 272 bytes of Z80 assembly. That's how much it takes up in memory. So you can see straight away we've already got a significant saving from 272 bytes down to 81 bytes of use. Now of course memory use is only one aspect of this. Performance is also critical. And I am tracking as I build this where performance is going. So you've got the overhead of running in a virtual machine, so reading each instruction out of the memory data, interpreting which instruction it is, jumping to the right place, executing the code. Now in reality a lot of that same functionality is probably going to be present in the surrounding code for this as it's compiled from C. So I'm not concerned necessarily about the performance there, although I am keeping a track on it and making sure that it doesn't get out of hand. because it's going to be a balancing act between how much memory it uses, how performant it is, and how practical it is for users to work with. And obviously the being able to track exactly how much memory you've got available and every byte you use for sprites or tiles or whatever contributes to that is a really, really important feature for Kwyll to be able to implement if possible. So just to see how it works, I'll do a quick export from here. And the other aspect of exporting with less code and mostly data is that the compile time at export is much, much faster, because the only thing it needs to compile is data blocks. Eventually it'll only be compiling mostly data blocks. All of the core functionality of Kwyll is in the library, which is pre-compiled and delivered as a binary. So if I export this now, you'll see just how much quicker, anyone who's seen it before or seen any of the previous videos see how much quicker it is, a few seconds to do the full export, and that's only going to get faster. It may even get to a point where there's no compile necessary, where I can export a binary directly from Kwyll and combine it with the library in some way, but that's for the future. So now if I switch to the emulator so I can show you that it works. So you saw how it worked in the simulator, so same thing. The blue bars on the side are for my information for tracking performance. So this is what I was saying about how I'm keeping an eye on how much of a performance hit using the virtual machine is. But you can see that everything's working. It is a little bit slower than the C version, but I've got ideas to improve that. And you can collect the key and it disappears off screen. So that sequence of code is running entirely within the virtual machine with no compiled code at all, and seems to be working as planned. So there's one more aspect of the implications of this potential switch in direction, is and how it affects the memory availability. Is of course the virtual machine contributes code to the library, which wasn't there before. So while you're not generating as much C code from the export, you are carrying an extra load in the library for the virtual machine that runs the code. Now that at the moment is running at around about 2K, but I've got a lot of ideas where I can optimize that for both performance and memory use. Ultimately, the aim will probably be to hand tune the virtual machine in Z80 assembly. At the moment it's in C because it's convenient to work that way. Makes it very easy. So I've been able to get to where I am now in about 8-9 hours worth of total work combined, which I wouldn't have been able to do if I was hand coding the VM in Z80 from scratch. So there are ways to mitigate that, and I'm sure as I continue down this path I'll learn a little bit more. I'm hoping this is going to be the solution, because I think the value that it brings to the game designer in understanding how much memory availability they've got and what they can work with is absolutely paramount. It's super important, and finding other ways of doing it is very complex with the old C method. So I'm hoping this is going to be a viable solution. But as with all this, welcome any comments, any thoughts from more experienced Spectrum developers. So if you see this here and it gives you any ideas or shivers or makes you think what on earth are you doing, let me know, and or even better, pop over to the Discord and we can have a chat there, and you can tell me what I'm doing wrong or right. So if you like this, if you want to see more of this sort of low level deep dive technical videos, then let me know. I'm happy to do more of these and give you a bit more of an insight into the under the hood stuff, if that's what you want, or if that's what anyone wants. And if you like what you're seeing, don't forget to subscribe and leave a like, and pop over to the Discord and say hi, and I'll see you next time. Thank you everyone.